Swayam Prabha. Digital India. Educated India.
Okay, so let's start today's lecture with reviewing the forces and torques on the magnetic field systems. I am doing this basically because I do not want you to be so to say lost in equivalent circuits and things like that, which I will be very soon developing for induction machine and so on. So, they are what we use, but a bit of understanding of the physics of the system or the kinematics or the electromagnetics of the how the forces are generated, how the torques are generated, what is the energy interaction which is going on is important. I mean, because induction machine or synchronous machine have a very specific geometry associated with that. So, we develop something very specialized for those theory for those particular machines, but yet it is based upon the general notions of I mean, they are fundamentally based upon the physics of based upon the law of conservation of energy, the interaction of charge and electric field, the charge and the magnetic field, and then that is what built on it. So, what I am trying to sort of say is you can have a micro level development and then do a aggregation of it and get to a macro level, or you can directly start from a grand macro level kind of a thing. So, aggregation is for a machine somewhat difficult, like to calculate count torque on each of the conductor and then do a vectorial addition of the torques and then calculate. So, that sort of becomes a bit tedious to carry on. So, at some point of time we will have to give up we will have to let go, if not give up is not the right word, but we will have to let go this approach based upon calculating the directly the force on the conductors and things like that. But let us do it for some time to get a insider's feel before we dive deep into the again we come back again to the induction machine which we have started. So, the Lorentz law which you must have studied in your physics, very much sure about that, says that force, which is a vector quantity, is given by q times of E, the electric field, into V times of B. So, here q is the charge in coulombs, E is your electric field, its unit is volt per meter, V is the velocity of the charge, everything in of course SI units, velocity of charge, its unit is meter per second, and B is in Tesla, Weber per meter square. Now, in this in this if you look carefully, you would see that if you look carefully, you will see that this is a cross product, is it not? This term is a cross product, and so you are taking cross product from V to B. So, if you had, this could be explained either by using a right handed screw, which I have sort of used earlier also, that if I have so let us say for example, let us take a specific case that this is V, this is my V, this is my B, and this will be my oops, this will be my F. So, one way of explaining it which I usually take is that I take a right handed screw and then rotate it from V to B, because it is a V cross B, and I see which way it is moving, and it is moving towards me. So, therefore, F is like that. But many of you must have also studied and known that this can also be figured out from the right hand thumb rule, which is to say that you take this in the direction of V, the thumb is pointing in the direction of V cross B, V comes first. So, V is, thumb is pointing in the direction of the V, the index finger is pointing in the direction of B of the right hand, and then where is the middle finger pointing? The middle finger is pointing in the direction of F. So, the middle finger points in the direction of F. So, you can explain it from this way also. Now, force due to electric field, is of course, and force is in Newton's, So, force due to electric field is of course in the direction of E itself. For a positive charge, it is in the direction of E itself. So, this part is pretty much straightforward, but and it just depends upon the given a electric field, it only depends upon the magnitude of the charge. But force on the due to the magnetic field, the other component which is sitting here, that is a cross product of V cross, that is cross product of V and B. So, it is, its magnitude is going to be V B sin theta, where theta is the angle between V and B, and machines usually we will keep it, geometry will give us a 90 degree or so, but in general it is angle between V and B, and direction is of course determined by the right hand screw rule or the right hand rule that we just discussed. So, force here is not just is not just dependent upon the magnitude of Q given a particular B, it is not just dependent upon the magnitude of Q, but it also depends upon velocity. Velocity of course has a direction also and a magnitude also. So, it also depends upon the magnitude and direction of the V. The direction of the V figures out how it is relative to the B vector, because we are talking in terms of V cross of B. Now, this sort of becomes, if we do not worry about, if we do not have a electric field to worry about, then the Lorentz force will come down to, for a given charge it will come down to V cross B. But this is also slightly inconvenient, because it is only dealing with a charge. Our problem is sort of much more complex, because we are dealing with currents in conductor, but this idea that is expressed here can be generalized when we are talking of large number of charged particles which are in motion in a conductor, for example. And we can rework this and show that F is given by J cross B, and now the unit is newtons per meter cube. Force it is the density of the force, where J is current density vector. So, its unit is amperes per meter square, and B is in, of course, Tesla. So, the B is still going to be in Tesla. So, see, if you multiply this by cube, a meter cube, that means what I am saying is, if you dimensionally check this J meter cube, then J is coulomb per meter square per second, because its current, its the current density, multiplied by m cube. I am not deriving it, I am just giving you a dimensional check to show that it looks all right to us. Then this becomes coulombs meter per second, which is nothing but the which has the dimension of product of charge, which has the product of charge and velocity, because the velocity is in meters per second. So, you can see that it is moving, when I multiply it by m cube, then it comes back to the original, this particular equation. Now, let me just take one example, basic example. This geometry comes again and again. So, let us do this simple example. We have a non-magnetic rotor. So, what do I have? I have a non-mag. So, we are discussing a very simple example now. So, what we have got is a non-magnetic rotor. We have got a non-magnetic rotor which is containing a single coil. Okay. So, it has a single turn coil, and it is placed in a uniform magnetic field of magnitude B V. So, it is like this. I have copy, best is to copy it and paste it again and again. Okay. So, I have placed, this is my direction of my B vector. Okay. This is my direction of my B vector. Let me make it a bit longer so that I can draw a circle easier. And this, okay, good, the circle in one shot came out well. So, I have a conductor sitting here, a turn. So, this is the center, this is the radius or the diameter of it, and here is a conductor sitting cross, and here is a conductor which is sitting with L sitting there. Just to make let it be like this. Okay, so I have this conductor carrying this. This axis here is my x axis or x axis or whatever, I x, and this is the direction of the radius I r, and the tangent to it is my direction called the I theta direction. Now, this is my wire carrying current I. The wire is carrying current I, and wire is carrying my current I, yeah, and the wire 2 also of course carries the same current I. So, it goes up from this turn and it goes down from the cross end. So, it goes down from the other end. Now, our question is, we are given certain numbers, let us take those numbers. I have I as 10 amperes, I have B as 0.5 Tesla, and I have R as 0.1 meters, and I have the rotor length of rotor is 0.5 meter. So, it is 5.5 meter long, and my question is, what is the torque rotational, that means on what is the torque which is acting on this turn. This is my this is the question that I am having. Let us say that this angle is alpha. So, what I have got here, if you look at it carefully, this angle is alpha. So, if I put something like this here, this angle will also be alpha, and then I draw a tangent here to take this direction I theta. So, this angle is 90 degrees. So, this angle is going to be 90 minus of alpha. Now, B is in this direction, okay. B is directed in this, and so the Q, what we have to do is, the current is going inwards. So, the current direction is given by the cross. So, this is my cross direction. This is the this is my direction of this. So, when I run the right handed screw from V to B. So, when I run the right handed screw from V to B, I will get the force to act from in this direction, right. So, I will get the force force from V, which is directed downwards, to B. So, if you use the right handed screw, V, B, and then the index finger is pointing out, middle finger is pointing outwards, or if you take the right handed screw and take from V to B. So, the force will come out, like this. So, basically it will tend to drive the omega in this way, is it not? I mean, so again, if this is the force, let me look at it this way with respect to this figure which I have drawn here. Let us say that direction is just means this side or that side, just makes it whether it runs clockwise or whether it runs anti-clockwise. If the force is directed around the horizontal line, I can break it into two components. One is around the radius vector and the another is around the tangent vector. So, therefore, I can resolve this force into two perpendicular components. I can resolve this force around two perpendicular components, and I can resolve this force around the two perpendicular component, and this is the component which is going to cause the rotation, and this component is not going to cause anything, it is just pushing pressure on to compress it, but it is not going to cause any movement. So, the rotation is going to come from this component. So, for that, if you look at this, I said this angle is alpha, this angle is 90 minus alpha. So, projection, to take projection, you will take cos of 90 minus alpha, which will turn out to be equal to sin of alpha. So, therefore, the F, the force which is going to act on it is going to be I cross of B, unit being, I mean, we write it, usually you must have also come across ILB. So, when L is not there, the unit should be taken as Newton per meter, which is to say that in the J cross B, the J has been multiplied by the area of cross section, that gives you I, and so there the unit was Newton per meter cube multiplied by area of cross section, then you get vector I times, but because the per meter cube is multiplied by area cross section, so it becomes n Newton per meter cube into meter square, which is Newton per meter. And if further, when you will apply, say that okay, my conductor is of length L, then it will further get multiplied by length L, and then finally, if this angle is 90 degrees, it will translate onto ILB, otherwise it will be L cross I times of B, this is what it will be. Okay. So, now now what is the angle between, in the cross product, what is the angle between I, which is directed inwards, and B, which is directed on this plane of paper. So, it is actually it is 90 degrees. So, therefore, F theta component, the tangential component that we are talking of, is going to be equal to, for the length of the conductor, ILB sin of alpha, because cos of 90 minus alpha is sin of alpha, and this will create, I mean, this will create a rotational force on this side, and the other side is also creating a torque or a rotational force on the other side, and so the total torque of the torque which you will get will be 2 I L B into R sin of alpha, which if you substitute it here will be 2 into 1.0 into 0.5 into 0.1 into 0.5 sin of alpha, which is 0.5 sin of alpha Newton meter. So, now you come back to this figure, this torque will become is a function of sin of alpha. So, this torque will be maximum when you are sitting here, this torque will be maximum when you are somewhere here acting like this and this, and when alpha becomes 0 it is completely directed along these lines. So, it will not cause any rotation to happen. So, this is a good example, this is a good example to show how a magnetic field interacts with current and creates a rotational torque, on a coil which causes the rotation. This is the very rotation that happens in all the motors, and the generators. Okay. Now, let me come back to something a basic electromechanical relay. So, what I have got here now is a V voltage source wound on a coil, I am sorry, voltage source which is connected to a coil with a resistance R. The induced EMF is shown as plus minus E. Look at the polarity clearly, same as equal and opposite to V. Of course, you have to adjust for the RI drop or the current which will take place here. This is a plunger kind of thing, hinged is here. I have said that this is a massless magnetic armature. Basically, that means we are not worried about if it picks any velocity or whatever. We are with this half of mv square will continue to be 0, and this will tend to set up a flux line like this, because we are assuming the magnetic core to be of infinite permeability. So, the lines of flux will try to this, and this is going to try to pull this plunger on this side, this plunger it will try to attract on this side. But what is happening is we are applying a mechanical source which is pulling it away in this direction, the positive direction of x. Now, we want to find out what if I am at some location x, I want to find out in this particular example how much magnetic field energy is stored in the air gap. This is what I want to work out. So, I am now I had one example on force, now I am going to have one example on stored magnetic energy. Later on I am going to connect both these examples. So, if you look at it, if the current I flows into this and a voltage E gets applied here, then the power which is being transferred, into this coil, leave aside what is happening, the loss which is happening in the resistor. So, what we are saying is power input minus power lost in resistor is equal to power which goes in the magnetic field in the setting up of the magnetic field. If we talk of energy, incremental energy in time dt, then it will have to be p times of dt, because p is dw by dt, the rate of work. So, the voltage applied here is V, the current which is flowing is I, voltage applied or rather voltage induced, more correct way we would be to say that the voltage induced is E. So, the power becomes I cross of E, and for a small amount of time dt, the electrical energy which is pumped into this magnetic system is going to be equal to I E dt, but E can be written by Faraday's law as d lambda by dt, and already the polarity of E has been so chosen in the figure that it is already opposing the current coming inside or growth of current inside the system. So, therefore, E will be written only as d lambda by dt, not as minus d lambda by dt. So, I substitute for E d lambda by dt times of dt, which means that W d W electrical, the energy, incremental energy which is pumped into the system is I times of d lambda. Now, if FLD is the mechanical source which is applied and a movement is of is dx, then the mechanical work done will be FLD into dx. So, this is what is going to happen, and so our equation will be that the electric field which we are pushing into, the electrical energy which we are pushing into it, partly used to do mechanical work. We are looking at it as if it is a motor. So, partly it goes to do mechanical work and partly it goes to increase the stored field energy dW field. So, d lambda is equal to dW field plus the work done, which is equal to FLD times of dx, or in other words, the field energy is the difference of the work done, the electrical input minus the mechanical work done. The electrical energy input from the source minus the mechanical work done is equal to basically the energy which is stored in the field, and I am taking this as a lossless system. So, I will come to that. So, if I want to find out how much energy is stored, my goal is to find out how much energy is stored in this configuration. So, if my magnetic field energy is stored in this configuration. So, if my goal is to work it out, then I should integrate this equation to starting from the in which. So, let us say that this is the lambda, see lambda and x trajectories could be many ways. I want to bring x to some default value x naught, and I want to bring lambda because I have this source. So, this is also I can control, and I can control this also because I have a mechanical source sitting here, I have a electrical source sitting here. So, I can bring this to a situation where it is at some distance x naught, and by controlling the voltage or effectively the current which is passing through it, n phi will give me the flux linkage as lambda naught. So, I want to set up this system to a equilibrium or rather a point which is corresponding to lambda naught x naught lambda naught. Now, I can reach this like this, I can reach like this, I can reach many ways. One interesting way is that I take a horizontal line along this x axis, this is path 1, this is path 2, 2A, and then I take a vertical path and reach here. Now, if I am taking this system as lossless and conservative, taking this system as a lossless and conservative, then this integral that we are talking of here is path independent. This integral that I am talking of here is path independent. If it is path independent, then the path that you chose to reach from here to here, I need not do the integration like that. I can assume that I took a convenient path like this, which is 2A, and then I went along the path 2B. So, I chose a path 2 times of A plus B, A and B, and then along each of these paths, A path and the B path, I calculate how much is the increase in the field energy, that is the integration along the given paths, and sum that, and I get the field energy which is stored at magnetic field energy which will be there at lambda naught x naught, our coordinate. Now, what is interesting about the path 2A? Along this path 2A, lambda is 0. So, what I am saying is simple. I am going to first, not as if here I will just have a switch which will be like open, for example. So, there is no current which is flowing there. So, current is not there. So, flux is not set up. So, n phi is 0. So, n phi is 0. Then just move this, actually you, because there is no resistive force and this is a massless thing. So, just pull this fellow to the position x naught, pull this fellow to the position x naught, and actually I am not doing anything serious in terms of work here. Then start increasing this voltage, assume that this is a controllable thing. So, start increasing this, or you could even think of it as a current source if you want to, directly a controlled current source, and increase it so that you come to the flux linkage which is lambda naught, and then you are set up for the lambda x naught lambda naught condition, and then you calculate what is the field which what is the magnetic field energy which is stored in this. So, in the path 2A, which is movement around this, d lambda is 0, because anything which is on the anything on this will keep lambda constant. So, d lambda will be 0, and because in particular we have taken it to be along the x axis. So, the exactly lambda is 0. So, therefore, the field FLD is also 0, and therefore, what we see is from in this component is also 0, this component is also 0, both these components are 0, and therefore, dW field, the increase in the stored field energy in this direction is 0. Unenergized system, just moving, very simple, unenergized system, nothing, no source yet connected, plunger is massless, just pulled it to the position x naught, there is no work to be done. We just showed it mathematically also that there will not be any work which will be required. Whatever will be done along the path 2B. So, along the path 2B, now what is happening is, the good thing is position is fixed. So, once the position is fixed, the magnetic geometry, once the position is fixed, the magnetic geometry is fixed. Once the magnetic geometry is fixed, what happens? Inductance gets fixed. We have already seen earlier also that inductance is simply n square by r. If the magnetic geometry is fixed, L is not changing, area of cross section, all those kind of stuffs are not changing, then the inductance for a fixed geometry, there is inductance is a fixed quantity. So, inductance will become fixed, and then only thing that we are doing is dx is also 0. So, because the dx is 0, so this component will not come into picture. So, whatever from the source electrical energy that we are pumping, that energy will just fill up, that energy will be just transferred as magnetic field energy. So, it will basically fill up your bucket in which you are storing the magnetic field energy, and you can just calculate that from the integral. So, therefore, dW field, because there is no mechanical work done because the position is held fixed, but to keep the position fixed, here as the current is increasing, see this is trying to pull this thing back here. So, that is why I have shown here, we have shown here a mechanical source, and we are assuming that it is automatically putting that thing on it, so that it does not move. It is equal and opposing thing it is doing, so that there is no movement there. Otherwise, what will happen is it will come and collapse, it will try to come and collapse here. Okay. So, by controlling both these sides, mechanical side and the electrical side, in this controlled experiment, what we are doing is we are making sure that we get a movement exactly around part 2b. Actually, to set it up mechanically may be much more sophisticated, but in this theoretical computational experiment, this is what we are doing. So, the field energy now which will be created, dW field, is just going to be I times of d lambda, because the dx is 0. So, no mechanical work is being done. So, whatever is put in the electric side is going into the field energy, and this integral should be done from lambda being raised from 0 to lambda naught, whatever is our default value. But because lambda is what, L times of I, right, the lambda is L times of I. So, I can write I as lambda by L of x naught times of d lambda, and then because this is a fixed quantity, so it is just integrating lambda d lambda, which is half of lambda square, taken from definite integral taken from 0 to lambda naught. So, half of lambda naught square by L lambda naught, but if you substitute lambda naught as L x naught times the corresponding current I naught and square it, then this will also come as half of L I square, half of L I square of this much amount of joules. So, this is the field energy which will get stored, in this thing, in this our electromechanical center. In general, this stored energy can actually be written as a product of dot product of H dot of B, half of H dot of B, the unit being joules per meter cube. So, you have to do a volume integral with respect to dV over the V, and if B is written as is a linear material or even non-linear is okay, but if it is just a linear material, then you can write it as B by mu, and then this equation will come out to this particular form. All right. So, let us now use this idea. Now we know that how much is the how to calculate in some sense the magnetic field which is stored in the air gap, and we have got some idea of that. Now, let us use that idea to calculate the force which will be created in a plunger or a electromechanical relay or something like that, basically electromechanical devices. So, I have a simple example sitting here. Is my magnetic structure, magnetic core, its permeability is infinite, it is connected to a source shown here by lambda setup. Inside, to set up a lambda carries current I, the winding or the coil has n number of turns, and of course considered lossless, everything here is considered lossless. Dimensions are shown here, this is D, this is L, this is L, a air gap of G here, air gap of G here. Now, the thing is, when I excite this thing here, start pushing the current, it will try to pull this plunger in, that is the action which is going on. So, somewhere in between we are taking a snapshot at a distance x. So, therefore, because this distance is d and this distance is x, so the overlap area is this overlap area is d minus x. So, you have d minus x along this, a length of L which is moving along this. So, the area of cross section which the flux lines will see is d minus x into L. Okay. Now, we have seen that if we freeze ourselves at some point x here, the magnet field energy which is stored is going to be half of L of x, which is a function of x, and the current I which is I of square. So, let us try to calculate the inductance L of x. So, turns are R. So, we know that inductance is given by n square divided by reluctance, and reluctance will be given by, see this has 0 reluctance, right, because I have taken permeability to be infinity. So, therefore, it has 0 reluctance. So, 1 by mu 0 air gap. So, G air gap here, G air gap here coming in series. So, therefore, total air gap which is coming in series is 2 G divided by the area of cross section. So, the area of cross section we have already calculated it as d minus x times of L. So, n square by R or the reluctance or calligraphic R if you want to be very particular about it, then L of x will be n square divided by 2 G mu 0, and this d I am taking it common, d minus x into L, I am writing it as d into L into 1 minus x by d, because x will be between 0 and d only. So, that is why x by d will be a fraction between 0 and 1. So, L of x can be written in this particular way. So, then substituting this here in half of L x times of I square, the field energy will become half of n square mu 0 L d 1 minus x by d divided by 2 G, which is whole of this is L times of I square. This is the field energy which is stored. Now, let us assume that current is that we have set up is 10 amperes, the gap is 1 mm or 0.001 meters, number of turns are 1000, the dimension d is 0.1 meters and the dimension L is 0.2 meters. This is d, this is L, this is G, 3 important dimensions that we have to worry about. Okay. Now, I plug it in all this, I can immediately first of all calculate what I was talking in the previous examples. What is the field energy which will be set up as a function of x and x, and the field energy for this given current. Of course, the current is kept constant, remember the current is given to you to be 10 amperes. Therefore, it just turns out to be 628 1 minus x by d. So, okay. So now let us say that we want to calculate the let us say that we want to calculate what is the magnetic force which is going to be created. So what I go back to this equation, the incremental energy balance equation that we had written earlier, which said that whatever is the electrical energy pumped into the electrical energy which is pumped in minus the mechanical and incremental work that gets incremental electrical energy pumped in minus incremental work done should be equal to the incremental field energy stored in a lossless system. Now, what I will do is I will so this is a function of lambda and x, that we have already seen that the stored field energy is a function of lambda and lambda and x are my two independent variables. Lambda I am able to control by using my source, and x also I am able to independently control. So, therefore, lambda and x being two independent variables, I will take partial derivative this dWFLD. I can write it as partial derivative of the field energy with respect to lambda times d lambda plus partial derivative of the field energy with respect to x times of dx. And now, I equate this to this. When I do this equating this to this, what I should do? This, because this is true always, I should equate this and I should equate this. That means, what I am trying to say is I get that dWFLD by d lambda minus I times of d lambda plus of dWFLD by dx plus of FLD, or is it going to be minus or whatever, dx is going to be equal to 0. Just check that sign a bit carefully, but this is what I will get it. And since this is true for whatever d lambda dx that I am doing, so therefore, I can equate it term by term and I get that I should be equal to d field by d lambda and FLD should be equal to minus of the partial derivative of W field with respect to dx. So, now we calculated that W field is half of L of x times of I square. Since I am working with lambda x system, I will try to rewrite it by multiplying once by L on the top and bottom. I will rewrite it as half of lambda square of at a given position or whatever divided by L of for a given current divided by L of x. So, and now this lambda should be fixed. When we are calculating the force, it is a partial derivative with respect to x. So, it is as if the lambda is fixed, and then we calculate FLD as minus of del W FLD by del of x. So, the lambda square, because it is in the partial derivative, it is not partial derivative with lambda, it is only partial derivative with x. So, this will be taken out as constant, half will be taken out as constant. So, you are just looking at partial derivative of this with respect to x. So, first you will do what? Partial derivative with respect to L and then partial derivative with respect to x. So, therefore, 1 by L square minus 1 by L square, and that minus will cancel out and give you 1 by L square times del L by del x. Now, del L is already here. Where is L? L is here. So, del L with respect to del x is going to be n square mu 0 L d by d. So, d and d will cancel out times 2 g into minus of 1, because 1 minus x by d. So, therefore, into minus of 1. So, the d and d is again cancelling out, and So I get basically partial derivative, I just substituted that here, and I get this as minus of n square mu 0 L by 4 g into I of square. And when you substitute this all the required numbers here, you get this as minus 6280 newtons. So, it is attracting, its x is in this direction, it is pulling it in this, it is in this direction. I think these numbers you can easily check up. This is 4 pi into 10 to the power 7, n is 1000, so 10 to the power 6. So, 10 to the power minus 7 into 10 to the power 6 became 10 to the power minus 1. L is given to you as 0.2, current is 10 amperes. So, the square of it becomes 100, 4, and the gap is 1 mm or 0.001 meters. So, therefore, this F is a attraction force of 6280 newtons. Now, the interesting thing that I want to see is that you do not get the, if you directly do this from here, sorry, if you directly do this, you do not get that number, you will get something like minus 628 by d. Yeah, you get it, I think, no problem. Yeah. So I think I need to just a minute. Let us do this. So, dWFLD by dx will turn out to be minus 628 by d, which is minus 628 divided by 0.1, which is minus 6280 Newton. So, you could actually in this particular you could also get the same answer by doing this, but this way, the way I have done it is usually the way you will find we calculate in most of the machines, keep lambda constant and take partial derivative with respect to x, but we just cross because we had done the complete simplification earlier also, and we had just seen that because the current was kept constant and the field was therefore just a function, WFLD was just a function of x. So, therefore, we could have also calculated from there. Let us take a break here, we will continue in the next class. Thank you.